on schedule. So I'll take a look at that again. But anyway, if that is the case, that gives us a lot of extra time for just like AP specific question reviews and how to kind of like approach the test. So today we're going to go over the questions that you guys requested. I'll post another video, hopefully tonight or tomorrow, with the problems that will take a little bit longer. So I was kind of shocked at the amount of questions, but maybe it's just because I haven't had you guys post all questions, misconceptual questions, and problems all in one shot. So if you weren't aware, there are solutions on Schoology, which I think a lot of the misconceptual questions and question solutions do a good job at explaining, but we'll go through them anyway. So make sure you have a textbook available, meaning online textbook, and we'll go through. So the first one was question 2 of the questions. This one was with the blue truck and the box sitting on it. So a box rests on the frictionless bed of the truck. The truck starts driving. The truck driver starts the truck and accelerates forward. So we have acceleration. So little thing. Net force is going to play a factor here. The box immediately starts to slide towards the rear of the truck bed. Discuss the motion of the box in terms of Newton's laws, as seen A, by Mary standing on the ground beside the truck, and by Chris, who is riding in the truck bed. So this is all about relative motion. So this is 2. Don't laugh at my truck. Let's see here. There we go. So we got the 2 people. Let's label them. What's their names? Chris and Mary. So Chris is on the truck and Mary is off the truck. So when the truck takes off, the box is going to not want to move. So the focus here is the box. The box has inertia. It has mass. It has a resistance change in motion. So since there's no friction on the truck bed, there's no reason to cause the box to move forward. So in a scenario where the box doesn't have any friction, it will actually stay there. And after the truck goes to the right, can I do this? After the truck goes to the right, oh, that worked awesomely. The box will fall straight down because there's nothing causing it to move to the right because there's no friction. So this is that, age-old magic trick where you have all the silverware and flowers on the table with a tablecloth, and the magician pulls the tablecloth very quickly and everything remains. So even if there is friction, if you move the object quickly, or like the tablecloth, if you move the tablecloth quickly, you can overcome any friction because that object that's at rest on top of the tablecloth has inertia and does not want to move. If you do so slowly, then it will fall off. So in this case, if it was a truck and there was friction, if the truck slams on the gas, slams on the brake, turns very quickly, the box will slide around the back. But if you do so slowly, where you allow some time to have friction take effect, it will move around. So for part A, Mary standing on the side, it's like the box doesn't even move, right? Because the box stays here and Mary stays here. The box just seems to fall straight down and no horizontal motion apparent to Mary. But for Chris, it looks like, since Chris is on the truck, I think in the picture in the textbook kind of does it a little bit better, that he's holding onto the truck. The truck moves to the right, but the box doesn't move with him. So it looks like the box is moving or accelerating. So this question was just all about relative motion. The next one that people brought up was number 9. Sorry, I got a text that I am able to get a Grinch costume. Nice. For the holiday to show Kellen while he's in the hospital. Sweet. So number 9, this was the stone hanging by a string. So here's the stone, and then there was another string that we're going to pull down. I'm going to post a video to Schoology after I upload this video that will kind of help the explanation of this. But basically it is, if you pull slowly, the top string will break, because you're going to have, let's use another core. You'll have the tension going down on the rock, plus the weight or force due to gravity on the rock. So if you pull slowly, that top string will break. However, if you pull quickly, the bottom string will break, because the rock has a resistance, it has inertia, it has mass. So if you pull quickly, it's not allowing, both the tension force and the weight of the rock to have an effect. Kind of like the last problem with friction. So friction really needs some time to have an effect. You can overcome friction, mainly being if you move things slowly, static friction takes place. If you move things quickly and sliding is taking place, not necessarily sliding here, but it's a similar idea, it's more of a kinetic friction. Let's see, then we got 11. And that line's bothering me. So this reads, part A, you pull a box with a constant force across a frictionless table using an attached rope held horizontally. So here's our scenario. We got a table. Go below. Got a box that we're going to pull with a rope, and we pull in this direction. And it is a frictionless table. So now, that's our initial scenario that we observe. But now we're going to pull at an angle to the horizontal. What's going to happen to the acceleration of the box? Will it increase, decrease, or remain the same? So if we pull upward, as drawn now, when we look at the components compared to the original scenario, our X component, this will probably be like tension, I guess, or applied in X, that's going to be smaller than that original force. So the acceleration would decrease. So that's part A. Part B, what if there was friction? So what influences friction? The mu is not going to change because the surfaces are the same, but the normal force will change depending upon the angle. So the greater the angle theta that I just put in there, the less and less X component will have, and the more Y component you'll have. So the more Y component you have, normal force will decrease, because the upward Y component of tension is supporting the downward, or it's taking some weight off of. So if we drew a force diagram for this scenario, you're going to have a little bit of normal force. Don't know why I wrote that really weird. So you have your X and Y components of tension. So the greater the angle you have, the more tension vertically the Y component of tension has. So that means normal force can decrease. So the greater the angle that you have of that rope or whatever, the less friction you're going to have. But then it's as a trade-off. Like you'll have less friction, but then also the Y component will decrease as well. So for part B of that, if there is friction, as you increase that angle, the acceleration will decrease because you have less friction, but at some point it will start to decrease because of that whole X component. So kind of like with projectile motion, 45 degrees being that sweet spot with having the most out of your X component to get your velocity and then the most out of your Y component to get your time. Same thing here. We need to find that sweet spot for getting the least amount of friction, but then also the most amount of horizontal force causing the acceleration. So depending upon the angle and the scenario of the problem, it will change. So then we're on 13. Go back to my original color here. 13 says, compare the effort or force needed to lift a 10 kilogram object when you are on the moon with the force needed to lift it on Earth. Compare the force needed to throw a 2 kilogram object or 2 kilogram object horizontally with a given speed on the moon and the Earth. So what's the difference between the moon and the Earth? We haven't really jumped into universal gravitation, but we all understand that there is less gravity on the moon from what we've seen in videos. We know people have walked on the moon, they kind of bounce. So it's going to be easier on the moon to lift things straight up because there's less gravity. So you can look at that as like a force diagram. So this would be some kind of lifting force or applied force going up. So whereas G on Earth if I could spell right, is 9.8, so that would give us a bigger force. And I believe it's 1.6. Let me do a quick search. I always forget this. Yeah, it's 1.6. So G on the moon is a lot less. So it will weigh less. If something weighs less, it's easier to pick up, less effort, less force. So what about horizontally moving this object? So horizontally moving the object, we're not really concerned with the weight of it. We're just looking at the overall mass or inertial mass of the object. So if we're saying something has a mass of 2 kilograms, that 2 kilograms can be related to the inertia or the resistance to move it. So whether you are on the moon or on Earth, to throw an object that has a mass of 2 kilograms, it has actually the same level of difficulty. The same force would be required to accelerate at the same amount on both the moon and Earth. Now, there's probably more going into it that, you're not used to gravity on the moon and like the logistics of all the inner workings of your body, your biomechanics to throw it would probably be harder on the moon. But just simply said, it's going to be the same, both the moon and the Earth, for moving it horizontally. Let's go back to, here we go. So it's 13. Now we're looking at 17. 17 says, Mary exerts an upward force of 40 newtons to hold a bag of groceries. Describe the reaction force, Newton's third law, by stating A, its magnitude, B, its direction, and C, on what object it's exerted, and D, by what object it is exerted. So I think here it's easy to draw a picture. Don't laugh. That's my grocery bag. So, and then, actually I'm going to erase that. I'm not going to embarrass myself by drawing a person picking up a bag. Feel free to do so yourself. So just imagine picking up a bag. So let's say this bag, let's draw a force diagram wise. I'm good with basic shapes. So we got gravity, it weighs 40 newtons. Down. It says Mary exerts an upward force of 40 newtons to hold a bag of groceries. So she's just holding it, not moving it. So Newton's third law, Earth pulls the bag down, Mary pulls the bag up with the same amount. So part A, 40 newtons. Part B, Newton's third law pair, Earth pulls it down, Mary pulls it up. The direction's up for part B. C, on what object is it exerted? It's going to be the bag. So again, our object of focus is the bag. So we're going to have our two forces on this bag. Or you can look at it, wait, here exerts. Oh, I'm sorry. The reaction force. So part A and part B, on what object is it exerted? So the reaction force, sorry, I'm tripped up in the words here. So depending upon how you look at it, we're looking at not Earth, but the bag and Mary, because that's how, sorry, I got tripped up in the wording. So bag pulls on Mary, Mary pulls on bag. Forces are the same. Now, she can accelerate it up. When she accelerates it up, the forces are the same. It's the same 40 newtons, you know. She pulls 40 newtons up, the bag pulls 40 newtons down. But there's other things going on with gravity. So anytime you see a Newton's third law, it's helpful to draw both pictures. So just because I was a little confusing. Here's Mary. She's holding the bag. Those are our two objects that we're talking about. So we're not really focused on the fact that, you know, there needs to be a greater force to accelerate it upward or downward, depending on which she's doing it, because we're leaving Earth out of the picture. So when we draw force diagrams, it's the forces on that specific object. When we talk Newton's third law pairs, it's the interaction between those two objects. So in this scenario, there's actually multiple conversations we can have with, you know, bag, Mary, Mary, bag, bag, Earth, Earth, bag. So either way you describe it, when you're mentioning those pairs, they have to be the same forces. So when you say Mary pulls up 40 newtons on the bag, bag pulls down 40 newtons on Mary, you can have the conversation, well, then how the heck does this thing ever move? It has to do with having that third object, the Earth, in there. So sorry for being a little bit confusing on that one. What's 20 say? 20, a block is given a brief push so that it slides up a ramp. So we have a ramp and a block. So it goes up the ramp to its highest point. So it will go some place up here and then slides back down. But the magnitude of its acceleration is less on its descent than its ascent on y. So if we draw a force diagram for the way up, all right, so obviously the forces that we're focused on are going to be in the direction of our incline. So we have our normal force, we have force gravity, and on the way up, we're going to have some kind of applied force. And then we'll also have friction going downward. So since we have an incline, we're going to have to break up gravity into components. Not bright enough. So gravity is going to have its components. So on the way up, we're going to have force of friction going down the hill. Also, force of gravity in the X direction going down the hill. And then we're going to have, so as far as we're just looking at net forces. And then this applied force going up. That's going to cause, oh, sorry, I didn't mean plus there. It's going to cause our mass to accelerate. When we're going down the hill, however, we're not going to have this applied force. You'll have a frictional force going up the hill, which would be the same as going down the hill, whatever value that is. So when it goes down the hill, you'll have friction plus that negative, it's just a direction, component of gravity. So this is up, this is down. So you can see by taking out this applied force, that means these two negative numbers add together to be a bigger quantity. So you have more force when it's sliding down, so that's why it would accelerate greater. So that was, what, 20? This is the last one, 22. What would your bathroom scale read if you weighed yourself on an inclined plane? Assume the mechanism functions properly even at an angle. So when you step on a scale, it's not measuring your weight, it's measuring your normal force. So think of like going to a bathroom scale and either pushing up on a counter, like there's like a bathroom sink or something that you push up on, it's going to read that you weigh less. Or if you had something that you could kind of pull down on, or like if there's a door handle and you pulled upward on the door, that would show that you would weigh more. But your weight would never change. So bathroom scales typically only measure normal force. So if you're not accelerating, you're just standing still, those two forces are the same. You can kind of see this way if you go on a scale and just kind of hop up and down a little bit to the point that you're not going to break the scale. But that weight will fluctuate. But really, your weight is not changing. So what about on an incline? So if this was your real weight, under normal circumstances, no pun intended, the scale, whatever your weight is the normal force. But if we tilt that scale, maybe your bathroom floor is at an angle, that number is going to be different. So where we're going to have to, I didn't want to use that one. Realign our X and Y. Where you would, real life scenario, you'd have friction here too, sorry. Forgot that out. So you'd have friction and the X component equaling your Y component of gravity would equal normal force. So since the scale measures your normal force, you would weigh less. So why is that important? For everyday scenarios, not really that big of a deal because people's weight fluctuates, a little bit, when you eat things, when you go to the bathroom, when you put on different size clothing, like sweatshirts versus t-shirts. But sometimes in the medical field and also for sports like wrestling, boxing, younger level football, it's weight classification. So I know that for wrestlers, their scales have to be calibrated before they weigh in, just so that everything is fair and they know that that scale is reading evenly for everybody. All right, so we're going to go ahead and jump over to the misconceptual questions as soon as I restart my laptop. There we go. So these are the misconceptuals. And I'm not going to go through every one as far as like choice A, choice B, choice C. I'm going to explain why the correct answer is correct. But feel free to bring that up in discussion during class tomorrow if you like. So misconceptual question number 4. And I don't like red. Let's go green. So this is the one with the bear sling. So the picture there shows 2 trees and the backpack hanging up so the bears can't get to your stuff. You might have food in there. And we're looking at the force needed to support. So let's just draw a force diagram for the backpack. So the misconception is that you can, if this was the backpack, you can have so much tension on this string that it's perfectly horizontal and you could support the backpack. That's the misconception people think. If you have this wire that's so tight and you hang something on it, it will support it. So visually, sometimes it looks like these wires or strings are perfectly horizontal, but they're not really. There's a small angle or small little sag or bow to that wire or string or rope. The reasoning is this bag weighs something. Force of gravity going down. So there needs to be whatever it weighs. If it's 5-pound backpack, there needs to be a total of 5 pounds going upward. Well, where does that force come in? Because there's no direct upward force here. So it comes from the vertical components of these tension forces. And the tighter and tighter you make the rope, the smaller and smaller these angles of tension get. But there's still, at the end of the day, needs to be an upward component. So you got your force tension Y, force tension, oops. So the X direction components of our tension are really what's, the resistance of the trees. If you made that too tight, those trees might fall towards each other. But we really need to explain or show that the sum of our upward forces equals our downward forces. So if this was perfectly horizontal, like most people think you can have, there would be no upward force. So there still has to be that small angle there. So hopefully that made sense. Next one is number 5. Get back to my normal colors here. So this is the guy in the gondola, it looks like. So 5, what causes the boat in figure 4-41 to move forward. So this is going to be a Newton's third law pair. So there's a force pushing backwards on the water. So if this is the paddle, you figure, do we even do the paddle? Let's see. So the man will put force applied on the paddle, or I think it can help say on the water by paddle. There's another force going forward. We'll just put applied force again. On paddle by water. So they're the same. So the problem comes, well, if the forces are equal, how is this boat moving? It's because of this. So this is an improper force diagram, because when we draw force diagrams, our dot is one object. But how I just kind of reason this out is that on the left-hand side, that force was on the water by the paddle, and on the right, it was on the paddle by the water. So we can't analyze it as far as force diagrams go, because then it would be, all right, the forces are always the same. Newton's third law says equal and opposite reaction forces. But it comes down to looking at the real scenario that for the boat, so obviously that's wrong. So if we just look at the boat, we can ignore the upward and downward forces. The paddle is pushing the boat forward. We'll just say paddle. Paddle slash water, because really it's the water pushing back on the paddle. And then what's resisting the boat? A little bit of friction. So any Newton's third law pair, the forces are equal, but you got to pick one object to look at or analyze. Next one, 7. Flying through here. We have a skier skis down a hill. The normal force exerted on the skier by the hill. So here's our skier. Again, I'm bad at drawing. Really lanky guy. Some skis. He's going down here. And the normal force, which we know is perpendicular to the surface, is going to act that way in orange, is going to be less than the weight of the skier. That makes sense because the weight's going straight down, and we know a little bit about drawing components. So this is like FGY, FGX. So these would be equal. And since, normal force is equal to the component of gravity, the hypotenuse is always bigger. So it's going to be smaller. So just because it's a multiple choice problem doesn't mean you can do some lengthy calculations or force diagrams. So I think we're on 9 now. Suppose an object is accelerated by a force of 100 newtons. Suddenly, a second force of 100 newtons in the opposite direction is exerted on the object, so the forces cancel. So something's moving, right? So we accelerate something. We don't know what it's called. 100 newtons. It's moving. It's accelerating because Newton's second law said if there is an overall force, it will accelerate. Then all of a sudden we bring in another force going the opposite direction of 100 newtons. Now we have no net force. So if there is no net force, there will be no acceleration. So if there's no acceleration, doesn't mean the object stops. It would continue at the velocity it had before the second force was applied. So to think of this, try and think of a scenario. You're driving in a car. You're at a stop sign and you're going up to a speed limit of, say, 40 miles an hour. So when you press on the gas, even though in this scenario there's, no force going backwards, in real life there would be a little bit of friction as you accelerate. And then when you get up to that maximum speed of 40 miles an hour, you can't just simply take your foot off the pedal. If you do, you're going to slow down. And you're not going to get to your place in time that you're going to. And if you go too slow, then that's also not good as well. So once you get up to that speed, that force of friction going backwards would have to equal the force going forwards for you to stay moving at that constant speed of, say, 40 miles an hour. You're pushing a heavy box across a rough floor, so hint, lots of friction. When you're initially pushing the box and it is accelerating, you got to pick which one of the scenarios are working. So D is the answer. The force you push on the box is equal to the force the box pushing back on you. So again, Newton's third law. So anytime two objects are touching, they are placing forces on each other, they are interacting with each other. So they're trying to get you to think like, how can you accelerate but have the same force? It's because for your force diagram, you're only focusing on one object. So when you draw your dot, that would either be you or the box. But in this scenario, they're saying, the force that you exert on the box is the force the box exerts on you. So you're mentioning two objects. So anytime you have an interaction between two things and you're mentioning both objects, the forces are the same on each. It's when you look at one object to focus on it is when you can talk acceleration and overall net forces. So that was kind of just a conceptual one. Newton's third law. 11, we have a 50 Newton crate sitting on a horizontal floor. So we can draw that out. Where the coefficient of static friction is 0.5. So we got a mu. It says that's static. And a 20 Newton force is applied to the crate acting to the right. What is the resulting static friction force acting on the crate? So one, we can say this is what they're trying to get you to do. And saying force of static friction. Mu is 0.5. We know if it weighs 50 newtons, force of gravity, they're going to equal. So normal force is 50. And you're going to say force of static friction is 25 to the right. Or I'm sorry, it's moving to the right, so friction's to the left. They want you to say part D, answer choice D. But that's wrong. So the reason why it's wrong, static friction, when we calculate it with the Fun equation, is a maximum force. So what you can do to kind of understand this is pick an object around your room, wherever you're sitting, a desk, a table, a chair, calculator, phone. Push a little bit on it horizontally to the point it doesn't move. And vary that force. Like push harder, push softer, so that it doesn't move. It's still at rest. So that force of friction that is opposing you is changing. So static friction can change depending upon how hard you push it. If you don't try and push it, there is no static friction. But with the equation that we have, the Fun equation, that's giving us a maximum force of 25 newtons, meaning if we apply more than 25, it will start to slide. So since in this case we know it's not moving, that 20 newtons that's applied to the right is equal to the 20 newtons worth of friction going to the left. And that's why it's a misconceptual question, because if you use this equation, again, that equation for static gives you the maximum force. I think we only got one left. 13, we'll go yellow, school color, gold, whatever you want to call it. And it's to pull a stump out of the ground. You and a friend tie 2 ropes to a stump. You pull it with a force of 500 newtons, which that's not that much, to the north while your friend, I guess the size of the stump, it depends. To the north while your friend pulls with a force of 450 newtons to the northwest. The total force of the 2 ropes, blah, 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 blah. All right. So north, 500 newtons. Northwest, so this is not necessarily a force diagram because we're doing tail to tail, but the total force from the two ropes is less than 950. So 950 is in all of them. So 950 you would get if they were in the same direction. So if, had this force, I can't rotate it, can I? I can. Both forces pulling in the same direction, they would straight up add together and it would be 950. But the fact that this is at an angle, you're not going to get, like, say we're like really trying to pull upward to the north. You're only going to get a portion of that 450 going in the same direction as the 500. So that's why we don't know enough to get the exact number, but we do know that it's less than 950. It's going to be more than 500, less than 950, someplace in between. So that was that one. That was more of a vectors problem. So hopefully I'll get another video posted for the problem soon. Again, if you have questions on any of these ones we went over, bring them up in class.